Shobir, please. Okay. So, hello everyone, and welcome to the European Non-Associative Algebra seminar. Today we have a talk by Andrey Lazarev from Lancaster University. He's going to talk on cohomology of Lie coalgebras. Please.
Thank you very much for extending an invitation to me to speak at your seminar. It's a great pleasure for me. Can I just ask, do I have 1 hour or there is a different duration of my talk? I wasn't sure.
Well, you have 1 hour, but this includes questions, so
Okay,
you know.
right. Okay, so I'd like to talk about cohomology of Lie coalgebras, which is a work in progress, joined with my long-term collaborator, Joe Chuang, and also Yun-He Sheng and Ron Kang. For those unfamiliar much with cohomology of Lie algebras or Lie coalgebras, I'm going to start with some preliminaries and recollections. Okay, so let G be a Lie algebra, just an ordinary Lie algebra, rather than a Lie coalgebra, or over a field K. K is generally assumed to have characteristic 0, and I will assume that as well, even though it's not written in my slides. And let M be a G module, which means by definition that there is a Lie algebra map from G into the endomorphisms of L, such as this. Using this map, G acts on L. Okay, so there is a Chevalley and Eilenberg complex, which I will denote as CE of GM, which is defined as follows. It's a group of nth cochains is the group of multilinear homomorphisms from G into M, which are skew-symmetric. So in other words, it's just homomorphisms from nth exterior power of G into M. Okay, so that's the group of nth cochains, and the differential is given by the familiar formula, which is written here. And I allowed myself not to specify the signs, which are well known and could be derived from the Koszul. Oh, was I muted?
Yeah, for a while, but now I can hear.
Strange. Okay, sorry about that. Okay, so I was saying that CE of GM is the Chevalley and Eilenberg complex of M, and its group of nth cochains is defined as the group of linear homomorphisms from the nth exterior power of G into M. The differential is given by the familiar formula. And the sign here, which I indicated simply as plus or minus, can be derived from the Koszul chain, Koszul sign. So here, F is an element in the nth group of cochains, and then therefore df will be n+1 cochain. So that's why we have n+1 arguments to be plugged in into df. All right, so the cohomology of this complex is called the Chevalley and Eilenberg cohomology of the Lie algebra G with values in the module N, or in the representation. So this construction is very well known. It's old. It belongs to Cartan and Eilenberg. It was formulated in the late 40s. And it has many applications in deformation theory and representation theory of Lie algebras. The low-dimensional cohomology groups of this complex have a natural interpretation as in equivalence classes of extensions, equivalence classes of infinitesimal deformations, and derivations. Lastly, I would like to mention that there is a generalization, an important generalization for some questions of this construction to the case when G is graded, in which case the signs, which I indicated as plus or minus, well, they're still plus or minus, but they're a little bit more complicated. There is also a generalization to the case when G as well as M are differential graded themselves. In this case, this complex is actually a double complex, where the second differential comes from the internal differential in G and in the internal differential on M. During my talk, I will occasionally refer to the differential graded case, but without loss of generality, you can disregard this, at least for the purposes of this talk. Okay, so that was the Chevalley and Eilenberg cohomological complex, and there is also an analogous homological complex. The difference is that, so just previously, we have here Homs from the exterior algebra. Here we have the exterior algebra showing up as a tensor factor, like so. So this complex, therefore, is covariant in G. The cohomological complex was contravariant in G. As far as the argument M is concerned, it's a covariant argument in both homological and the cohomological contexts. The differential in the homological complex is defined by this formula. Again, I take the liberty not to specify the signs explicitly. They could be obtained from the Koszul sign rule. And as before, there is a natural generalization of this complex where G and M are graded or even differential graded. Again, in this case, this complex will be a double complex. One of the most important properties of the Chevalley-Eilenberg cohomology, or homology for that matter, of a Lie algebra is its interpretation as a derived functor. To do that, let us recall that a Lie algebra G has a universal enveloping algebra, UG. So to any Lie algebra, there is associated an associative algebra. It's universal enveloping algebra, which is given by the following expression. So it's the tensor algebra. It's the free algebra generated by G as a space of generators, subject to the relations as indicated here. Okay. The functor of the universal enveloping algebra is left adjoint to the functor of the commutator Lie algebra, which is a more elementary functor. It associates to any associative algebra. It's commutator Lie algebra. And it is well known and easy to prove that modules over G, in the sense that I defined 1 or 2 minutes ago, a few minutes ago, they're the same as modules over the associative algebra UG. So representations of a Lie algebra G are the same as representations of UG. So this is a basic and easy result from representation theory. Then there is a similarly fundamental result belonging to Cartan and Eilenberg, which says that the cohomology, the Chevalley and Eilenberg cohomology of a Lie algebra is isomorphic to the cohomology of the universal enveloping in the following sense. Okay, so this cohomology is just X over UG from K into M. K is a module over UG. UG is well known to be augmented into K, where all the elements of G go to 0. So that's how K is a module over UG, and M is a module over UG, so we can form the X from K into M. And similarly, the homology, the Chevalley-Eilenberg homology of a Lie algebra G have an interpretation as a Tor form. So one consequence of this theorem is that the cohomology or homology of G with coefficients in M can be computed using any convenient resolution of K, projective resolution of K. And then the definition that was given previously as the cohomology of a certain specific complex simply makes use of a certain standard resolution, the so-called Chevalley-Eilenberg resolution of K. I'm not going to belabor that particular point any longer. And just as before, I would like to mention that with suitable definitions, everything that I just said, everything that's written on this slide also makes sense and is true for graded or differential graded Lie algebras and modules over there. For this, of course, you need to make sense of the notion of a derived functor for differential graded modules over a differential graded algebra, but this could be done. Okay, now let's move on to the things that were most were concerned in this talk. Lie coalgebras, their comodules, and cohomology. Okay, a Lie coalgebra, first of all, is a vector space G together with a co-bracket map delta, such as this, which satisfies a certain relation, which I'm not going to spell out explicitly, but it could be easily obtained from the ordinary Jacobi identity in Lie algebras by dualizing. Okay, so in particular, the dual map, which is the composite map from the tensor product of the linear dual of G into itself, determines the Lie bracket of G. In fact, if G is finite dimensional, then it is a Lie coalgebra if and only if its dual is a Lie algebra. So for finite dimensional Lie coalgebras, this notion is equivalent to that of a Lie algebra. For an infinite dimensional Lie coalgebras, this is not true. Similarly, a comodule over a Lie coalgebra G is a vector space M. So there is a typo here, together with a certain map, the co-action map, which satisfies a suitable analog of the Jacobi identity. Again, it means in particular that the dual Lie algebra G star acts on M star. I'm not going to spell out that axiom precisely, but it's easy to write down, particularly because it's just the dual of the ordinary axiom for the action of a Lie algebra on a vector space. Okay, so as I mentioned just a minute ago, the dual the linear dual to the Lie algebra is always a Lie coalgebra. However, the dual to a Lie algebra, oh, right, so there's another typo here. The dual to a Lie coalgebra is always a Lie algebra. However, the dual to a Lie algebra is not always a Lie coalgebra. And this is just because the dual to the Lie bracket is this map right here from G star into the dual to the tensor product of G with itself. And what we want is a map from G star into the tensor product of the duals. So the tensor product of the duals, that is to say, this space, it's in general smaller than this space. It's a subspace. So the image of the dual map to the co-multiplication, to the co-bracket, does not necessarily lie there. For the same reason, a Lie coaction cannot be in general described as a Lie coalgebra map such as this. So you can see that in the infinite dimensional case, the situation is a little bit more delicate. In the finite dimensional case, it's precisely dual. And again, all this generalizes to the graded context or even differential graded. Okay, maybe I should stop for a second and see whether there is any questions or comments regarding to what I just said. Okay. Seems not, so I will continue. So we've seen what a Lie coalgebra is and what a comodule over Lie coalgebra is. Similar to the Chevalley and Eilenberg complex for Lie algebras, we can define the Chevalley and Eilenberg complex for Lie coalgebras, and it is defined as follows. The differential in this complex is similar to the one on the homological Chevalley and Eilenberg complex of the Lie algebra. Imagine, for example, that the Lie coalgebra G is finite dimensional. In that case, G star is a Lie algebra, and this, at least disregarding the differential, will be isomorphic clearly to the nth group of chains of the homological Chevalley and Eilenberg complex of G star. And then I will just define the differential to agree with the homological Chevalley and Eilenberg differential. In the case when G is general, that is to say not necessarily finite dimensional, the vector spaces, the graded vector spaces underlying the complexes will not coincide, but they will be similar. One of them actually the graded subspace of the other, and the differential could be defined using so that they agree. Right, so the differential of the homological Chevalley and Eilenberg complex is similar, and it is similarly related to the cohomological to the homological complex of G star. Cohomological complex of G star. Okay, so again, in the case when G and M are graded or differential graded, all these complexes make sense, and they will be double complexes rather than single complexes. Okay, so with these definitions, the natural question arises, which I first saw in the paper which about Lie coalgebras of some Chinese co-authors whose exact names I unfortunately forgot now, but it's a relatively recent paper, and there they defined homology and cohomology of Lie coalgebras and gave interpretations of them similar to those for Lie algebras and coalgebras. Namely, they proved that certain low-dimensional cohomology groups have an interpretation as extensions or derivations. And there they mentioned in particular that it's not known whether those complexes have an interpretation in terms of derived functors. So that seems to be a natural question to consider, even regardless of whether there are any applications of that or not. But in fact, there are some applications. Okay, so once again, let me remind you that in the Lie algebra case, the Chevalley and Eilenberg cohomology have an interpretation as a derived functor in the category of modules over the universal enveloping. Okay, so the first thing to have is an analog of a universal enveloping coalgebra of a Lie coalgebra. And then, if we're lucky, we will be able to construct derived functors there and have an interpretation of the Chevalley and Eilenberg complexes in terms of those derived functors. So the construction of universal enveloping coalgebras of Lie coalgebras is more delicate than for Lie algebras, and somewhat less familiar. So even those who are not even much, don't even have much interest in the cohomology, they might be interested in this construction and various concomitant notions. So just as in the case of associative algebras, for associative coalgebras, there is an associated commutator or co-commutator Lie coalgebra. It has the same underlying vector space, and in the case when the dimension of this vector space is less than infinity, then it essentially reduces to the familiar construction of the commutator Lie algebra. So what we do is we dualize our coalgebra, take the commutator Lie algebra, then dualize back. In general, the co-bracket is still defined by the following formula. Okay, so we have an element C. We apply the diagonal to it, and then we subtract from it the diagonal where the tensor factors have been swapped. So the endomorphism tau is defined like so. Okay, so it's just swapping the two tensor factors, and one can show that that this formula defines a Lie coalgebra bracket on C. Then we have this functor, right? L of C, which associates to any associative or co-associative coalgebra, a certain Lie coalgebra. It has a right adjoint, which I will define by the same letter U, okay, as in the Lie algebra framework. And this functor associates to a Lie coalgebra G a certain co-associative coalgebra U of G. I'm not going to give here the definition or the construction of this universal enveloping coalgebra, but later on I will say a few words about this construction. Okay. For now, it suffices for my purposes to assume that such a functor simply exists. And then the idea is to relate the cohomology of a Lie coalgebra, the Chevalley and Eilenberg cohomology, to the cohomology of the corresponding co-enveloping algebra, enveloping coalgebra. That should be coalgebra. There is a certain amount of difficulties to overcome here. Firstly, you can ask, what are the derived functors in the category of comodules over co-associative algebra? We know what the functors Tor and X are in the category of modules over an algebra or a ring, but what are the corresponding notions for comodules? I'm not going to spend too much time on that particular question, but I'll just say that fortunately, this has been completely worked out, and it's not a completely straightforward question to answer, but it has been answered in the framework of differential graded Koszul duality, as constructed by Leonid Positsevsky. Right, so we do have X and Tors in the category of comodules. Sometimes they have been called cotor or coext. And in some limited generality, those functors have been known in differential homological algebra, and they have been used in various topological questions, particularly in rational homology theory. Okay, so that's one source of difficulty, which, as I tried to explain, is no longer a difficulty. And then the question is, what is the relation between comodules over G and comodules over its universal enveloping coalgebra? So let me just formulate the final result. And then I will spend the remainder of my talk explaining the ingredients of the proof and the terminology which is used in this result. Okay, so let G be a conilpotent Lie coalgebra. That has to be Lie. And M be a locally finite G comodule. In fact, the result is true in the much more general context of differential graded Lie coalgebras and differential graded comodules, but I'm not going to spend much time on that, other than just mention it here. Then the cohomology of the Chevalley and Eilenberg complex of G with coefficients in M is isomorphic to the derived functor of Hom in the category of comodules over UG from K into M. And the similar result holds for homology, for the Chevalley and Eilenberg homology. Okay, in this formulation, I mentioned conilpotent Lie coalgebras and locally finite G comodules without explaining what that means. Here's a definition. A Lie coalgebra G is conilpotent if it's a union of finite dimensional Lie subcoalgebras such that their duals are simply nilpotent Lie algebras. Another way to put it is to say that a conilpotent finite dimensional Lie coalgebra is just a Lie coalgebra such that its dual is a finite dimensional Lie coalgebra such that its dual is nilpotent. And then we can say that a general, not necessarily finite dimensional Lie coalgebra is conilpotent if it's a union of its finite dimensional conilpotent Lie subcoalgebras. Next, a comodule over G is locally finite if it's a union of finite dimensional subcomodules. So even though I cannot claim that the result holds in full generality for arbitrary Lie coalgebras and arbitrary modules, but it holds for this fairly wide collection of examples. So let me give you some examples which illustrate not the theorem, but the notions of a conilpotent Lie coalgebras and locally finite comodules. Well, the most the simplest, almost trivial example of a conilpotent Lie coalgebra is a finite dimensional Lie coalgebra with a zero covariance, or a abelian one. Such Lie coalgebra is conilpotent. Next, if we take a finite dimensional semi-simple Lie algebra and it's dual as a Lie coalgebra, then it's not conilpotent. For any Lie coalgebra G and any comodule over it, which if it's finite dimensional, then it's locally finite. And here's an example of a comodule that is not locally finite. So here's G, which is an abelian Lie coalgebra, which is actually one dimension, and it has the zero cobracket. Well, the one-dimensional Lie coalgebra must have a zero cobracket. If you look at the definition of a comodule over Lie coalgebra, then you can see that a comodule over it, it's just a vector space with an operator, with an endomorphism, just a linear endomorphism, nothing else. There is no restrictions on this operator. So any vector space M with an operator F on it is a comodule over this trivial Lie algebra. Now let's let M be infinite dimensional with the basis E1, E2, etc. And the endomorphism takes EI into EI plus 1. Okay, so we're here. Then clearly M is not locally finite. There is no finite dimensional subspace of M which is stable under F. Okay. So let me say a few words about motivations, about the motivation. Why do we care about coalgebras or Lie coalgebras? Well, about the question about co-associative coalgebras is actually very easy. They're very, very common, particularly to a topologist, and I'm a topologist, coalgebras show up all the time. For example, if you have any topological space X, then its singular chain complex is a coalgebra, differential gradient in fact. The diagonal delta is induced by the topological diagonal on X. Now, Lie coalgebras are more rare beasts. One source of Lie coalgebras, other than those which come from finite dimensional Lie algebras, okay, so one of those sources is rational homotopy. Given the topological space X, we can take the cochain algebra, say a singular cochain algebra on X, that's a differential graded algebra, and we can take its Harrison complex Unfortunately, I don't have the time to talk much about Harrison complexes, but it's a certain construction which is a kind of a bar construction of an algebra. And it turns out to be a differential graded Lie coalgebra whose quasi-isomorphism type encodes the homotopy type of X, the rational homotopy type of X, if X is a nilpotent, a rational nilpotent topological space. And then finite dimensional comodules over this Lie coalgebra, which is a differential graded Lie coalgebra in this case, correspond to a rational finite dimensional infinity local systems, which in different contexts are called chronological or locally constant sheaves on X. And the result, which I explained in the previous slide or slides, implies that the cohomology of such cohomological or locally constant complexes of sheaves can be computed using the Chevalley and Eilenberg complex. Okay, if you don't care too much about topology or rational homotopy theory, you can forget about that. It seems that as an algebraic structure, Lie algebras are quite natural and deserve a study in their own right, for their own sake. Okay, so let me say a few words about associative algebras and associative coalgebras. It's just a fact of life that they are very different, algebras and coalgebras. For example, we have the following fact, which is sometimes called the fundamental theorem of coalgebra. Every coalgebra, maybe differential graded even, is a union of its finite dimensional subcoalgebras. And similarly, every comodule over coalgebra is a union of finite dimensional subcomodules. It's a funny little property of coalgebras, and if you haven't seen this before, I recommend that you try to prove it yourself. This is not at all obvious how to prove. And I think you would spend maybe an hour proving that, at least. The thing is that this uses, in a very essential way, co-associativity. This is not true for Lie coalgebras or coalgebras of a different sort. Okay, so this property, which is that every coalgebra is a union of finite dimensional subcoalgebras, is not true for algebras. It doesn't hold for K of X, right? K of X, just a polynomial algebra in one variable, doesn't have any finite dimensional subalgebras at all, except for trivial, except for the zero subalgebra. So that means that duals to differential graded coalgebras are very special among all differential graded algebras. This fact, therefore, gets translated into something about the duals of coalgebras. We can reformulate it as saying that a DG algebra is dual to a differential graded coalgebra. We're here now, if and only if it's isomorphic to the inverse limit of its finite dimensional quotients. Such differential graded algebras are called pseudocompact. And then the coalgebra can be recovered from it as its continuous dual. Okay, so pseudocompact algebras and coalgebras carry an equivalent amount of data. They're equivalent to each other. If you have a coalgebra, then its dual is a pseudocompact algebra. If you have a pseudocompact algebra, its continuous dual is a coalgebra. Here's an example, okay? The formal power series algebra is pseudocompact, but the uncompleted polynomial algebra is not pseudocompact. Of course, all finite dimensional algebras are pseudocompact. Okay, so I already mentioned that the fundamental theorem of coalgebras does not hold for Lie coalgebras. And here's an example, which I probably shouldn't spend too much time on because it might take us a little bit too far afield. But here's an example of a Lie coalgebra which has no finite dimensional Lie subcoalgebra at all. Okay, so we just take the formal power series ring, we take its derivations. That's an algebra, but it's actually it's easy to see that it's dual to a certain Lie coalgebra. Okay, and had this Lie coalgebra satisfy this fundamental theorem, then that would mean that this pseudo-compact Lie algebra would be an inverse limit of its finite dimensional Lie algebra quotients. But it has no finite dimensional Lie quotient apart from 0. This may not be completely obvious, but it's not so hard either. Okay, so that means that associated to any Lie coalgebra, G is a locally finite Lie coalgebra. And that is to say, the just the union of finite dimensional Lie subcoalgebras in G. If we want to relate Lie coalgebras to its universal enveloping algebras, then they better be of a similar nature. Namely, Lie coalgebras must be locally finite if we want them to carry the same amount of information as their universal enveloping. Rigorously, what I'm saying is that the universal enveloping coalgebra of a Lie coalgebra is the same or is isomorphic to the universal enveloping algebra of its associated locally finite. This for this Lie coalgebra, for example, the universal enveloping algebra simply vanishes. So this is something that makes Lie coalgebras markedly different from Lie algebras. Remember that for Lie algebras, there is always an inclusion into their universal envelope. Here, it's not at all the case. It's possible for a universal enveloping coalgebra of a Lie coalgebra to vanish completely without Lie algebra being trivial. Okay, so this is the situation that we want to avoid. So we would like to consider only locally finite Lie algebras. And it turns out that for any Lie coalgebras, and we might as well consider only locally finite ones, there is an equivalence of categories of locally finite G comodules and comodules over the universal enveloping coalgebra. Okay, so that's the coalgebra or co-analog of the well-known result about Lie algebras and their universal enveloping. So for Lie algebras, representations of Lie algebras and one-to-one correspondence with representations of their universal enveloping ones. For Lie coalgebras, we have to consider locally finite representations or co-representations for this to be true. Okay, so in view of this discussion, we can make the following conjecture, naive conjecture. Given a locally finite Lie coalgebra and its locally finite comodule, that should be comodule here rather than a module, there is an isomorphism between the Chevalley and Eilenberg cohomology of G with coefficients in M and the corresponding derived functor of Hom from K into M. Unfortunately, this conjecture is false. It's false even for finite dimensional G and M, which is quite surprising. It was quite surprising to us when we realized this. Indeed, let's consider the following situation. G, the Lie coalgebra G, is just the dual to a semi-simple Lie coalgebra, finite dimensional. This is dual to a semi-simple Lie algebra. Okay, so a semi-simple Lie algebra, such as SL2, okay? We take this simple indeed, Lie algebra and its dual as a Lie coalgebra. Then the category of finite dimensional G modules is well known to be semi-simple. That's just saying that every finite dimensional G module is completely reducible. A little extra argument shows that the category of locally finite G comodules is also semi-simple. Okay, so there are no non-trivial derived functors. Every short exact sequence in comodules over the corresponding universal enveloping coalgebras splits. Okay, there are no non-trivial derived functors in the category of comodules over UG. On the other hand, the Chevalley and Eilenberg cohomology of G is the same as the ordinary Chevalley and Eilenberg homology of the corresponding Lie algebra, okay? And the Chevalley and Eilenberg homology or cohomology of semi-simple algebra, they're often non-trivial. For example, if M is a one-dimensional trivial representation, then it's well known that they're non-trivial cohomology, even for SL2. So this example shows quite definitively that we have to eliminate from our consideration semi-simple Lie coalgebras as well. So not only locally finite Lie coalgebras, but also semi-simple ones. One way to do it, if we want this result to be true, one way to do it is to restrict to conilpotent Lie coalgebras. Okay, so let me talk a little bit about conilpotent Lie coalgebras and their universal enveloping coalgebras. So recall that associative coalgebras or co-associative coalgebras are the same or equivalent to pseudo-compact algebras by linear duality. So they can be recovered from their duals as a continuous dual. Okay, so let G be a conilpotent Lie coalgebra. Then we'll have the following theorem, which is actually true in a slightly more general context, but we're only interested in conilpotent Lie coalgebras. So G is conilpotent, and we also assume that it's finite dimension, just for simplicity, not because we absolutely need it. Okay, so then the universal enveloping coalgebra of G has the dual, which can be described as follows. We take G star, that's just an ordinary Lie algebra. We take its universal enveloping, and then we pseudo-compactly complete it. So what that means is we take this algebra, and we take the inverse limit of all its finite dimensional quotients. Okay. Notice that this algebra, the universal enveloping algebra of G star, is augmented. All universal enveloping algebras of the algebras are augmented. And we can simply consider the much easier completion, the completion at the maximal ideal of this algebra. This construction, or its dual, phrased in terms of coalgebras, leads to a conilpotent universal enveloping coalgebras. And comodules over this coalgebra correspond to conilpotent comodules over G, as opposed to locally finite comodules. So this is a different, and I would say somewhat, well, rather simpler construction, and maybe not quite as interesting. Okay, so for a conilpotent Lie coalgebra, again, we assume that its dimension is less than infinity. We can dualize and consider G star, which is a finite dimensional nilpotent Lie algebra, and so it has a decreasing filtration, which is called the lower central, which is sometimes called the lower central series. This filtration has the property that the associated gradient to it is an abelian Lie algebra. In some sense, it's pretty much the same. This property characterizes nilpotent, finite dimensional nilpotent Lie algebras. Those are precisely those whose associated gradient to the lower central series give an abelian Lie algebra. If we dualize back, then we get that G, the Lie coalgebra G, has an increasing filtration, right? So if something has a decreasing filtration, then its dual has an increasing filtration. But again, the associated gradient is abelian. The strategy for proving the result, which I formulated a few slides ago, which is the main result, which that I was describing, is to work out the Chevalley and Eilenberg complex and relate it to the cohomology of the co-enveloping algebra in the abelian case, and then use this filtration kind of to bootstrap it to the general case. Moreover, if G, so that's one reduction. Making a bit of a leap, I would want to say that this reduces to the case when G is abelian. Furthermore, if it's abelian, then it's clearly a direct sum of one-dimensional abelian Lie coalgebras. And that reduces the situation further to the case of a one-dimensional abelian Lie coalgebra. Okay? So one could think that this is already completely trivial and obvious. I will just explain that this is not hard, but still not completely obvious. And a similar but a little bit more involved argument works in the differential gradient context. Okay, so let G be an abelian Lie coalgebra of dimension 1. What could be easier? It's just a vector space of dimension, right? And let M be a G comodule. So what is M? It's just a vector space with an endomorphism F. Then the Chevalley and Eilenberg complex, in this case, has the following form. It has two terms: the zeroth cohomology group and the zeroth cochains and one cochains. It's just because the exterior algebra on one generator is two-dimensional, has one, and it has the generator. Okay, so in both cases, the graded components of the exterior algebra is one-dimensional. So we have M in degree 0, we have M in degree 1. So we have a complex, two-term complex. M goes to M. And a little bit of a calculation shows that this differential is just F. One could also prove that this is also the complex which computes the X in the category of comodules over the corresponding universal enveloping algebra from K into N. For this, one needs to understand the universal enveloping algebra of this Lie coalgebra, abelian Lie coalgebra, and how to compute the derived functor of Hom in these comodules. And the key result here, still this is not completely trivial, even though one might be tempted to think that there is nothing to prove here. The theorem here is that for an abelian Lie coalgebra G, here I'm not actually assuming that it's one-dimensional, even though the one-dimensional case is all I need. Its universal enveloping coalgebra is the co-free coalgebra on G. In other words, what I mean by the co-free coalgebra, C of G, I mean that this functor is right adjoint to the forgetful functor from coalgebras to vector spaces. So this theorem makes the desired result at least plausible, because one could think that comodules over a co-free coalgebra are somewhat manageable, and that turns out to be the case. I have a couple more slides here, but maybe I should stop at this point because I'm almost out of time, and I still want to have a couple of minutes for questions. Just before I finish, I would like to say that the notion of a co-free coalgebra, as opposed to a conilpotent co-free coalgebra, is quite subtle. Okay, and that's what was the content of my next two slides. I was going to talk about the structure of co-free coalgebras, but I'm not going to do that because I'm nearly out of time. Thank you very much.
Thank you, Andrey. Are there questions? It seems that there are no questions. So thank you once again for this very interesting talk. Where it was given in a very accessible way, so it was easy to follow. And thanks for accepting the invitation. And so I guess
it's been my
we can
pleasure.
stop at this point. Yeah, thank you. I guess we can stop at this point and wish to all the participants a good week and have a nice day as well. See you.
Have a good weekend, everybody.
Next week.